seminar in the second term. I hope you had a good break and coming back energetic for the second term. And also for you new students starting this term, welcome. We are very fortunate to start the term with two excellent speakers from very distinguished company. I believe it's one of the most distinguished structural engineering firms, at least in Canada. So the two speakers, first, Dr. Tibor Kokai. He studied at Technical University of Budapest, structural engineering, and then worked in Vienna for 2 years. And then he moved to Canada in 1987, worked as a company called Whole Soul as a senior associate for 10 years. And also there was very strong company called Eolis, and he worked in Eolis for 13 years as partner. And then he joined RGC, where he is now as a principal in 2010. Then he worked on some world-class projects in Canada and also abroad in the United States, United Arab Emirates, in Europe. And he's definitely one of the most reputable and strongest engineers, structural engineers in the company, in the country. With 30 years of experience, he designed many tall and complex residential office buildings, and very big list of very impressive projects like Windsor Casino, Aura Residential Tower, 454 Yonge Street, the 1 Bloor West, and many other projects. And also he's very active in technical committees. So in the CSCE 823.3 on the design of concrete structures, I know that he's fellow at the Canadian Academy of Engineering, which is very impressive. And also he served on the committees for earthquake design in the National Building Code. Also he's active in research, like he has an intellectual properties for viscoelastic coupling dampers that he has developed with the University of Toronto, and it has been used in some structures, including 454 Yonge Street. So I know Tibor is considered as the reinforced concrete expert. Now I'm going to introduce the steel expert. Okay, I got to know that Andrew is the steel expert in RGC. I'm probably one of the experts in the country. So he works as a structural engineer at RGC and designing very unique steel structures, including residential, retail, commercial, and entertainment structures. Also, a big list of very nice projects, including Square One Shopping Center and West Expansion, Canadian Museum for Human Rights in Winnipeg, and also bridges. He worked on a number of very impressive bridges. Also, he is active member in the CSAS 16 for design of steel structures. So I think please welcome with me the two speakers, and I'm sure they're gonna talk to us about very nice, interesting project. So I'm gonna give now the floor for both of them. Okay, so Tibor and Andrew.
Thank you very much for the introduction, Dr. Dalmati. I will talk for the first 30 minutes and then Andrew will continue. First of all, greetings to all of you. Hope you're all well and happy. So let's start with this project, CIBC Square Phase 1, and we'll talk a bit more about Phase 2 as well. Touch upon that building as well. So the building, I hope this works. Page down, maybe. 1 second. There you go. The building is located downtown Toronto, as you know, near Union Station, Scotiabank Arena, etc. So the orange red is the site south of the Rayland, and you will see more details. So originally, Phase 1 is the tower, there's a parking lot, and then we have an overbuild we call it West Terrace or West Park over the rail corridor. As you see, the brown tower is phase one, the green is the podium. It exits to the right to the Young Street, and the podium is the purple, and phase two is on the north. We are confined with Gardiner Expressway, Bay Street, with the 18 Young Street condo on the right side. So the complexities are enormous because there's a TTC LRT tunnel, as you know, from Queens Quay. The streetcar goes underground, it turns up, it turns to here. And then the Gardiner with special foundations is an issue as well. The current GO bus station up on the top of the screen is right now operating from phase one podium. And that's an interesting proposition because the North Tower, phase two, the brown, which is phase two, the core fits at the current GO bus station, or the existing GO bus station, the previous GO bus station. But the columns cannot come down because they would be in the rail corridor. That's an incredible complexity. We'll talk about it. This project is 10 years, at least 10 years old. Ivanhoe Cambridge bought the land. Adamson Architects started, Adamson Associates Architects helped them putting the proposal together, and the whole scheme did an incredible job. And of course, the competition was won by Wilkinson Eyre, who are the design architects. So the two towers model is here, 2.9 million square feet. CIBC leased 1.75 million. Developers are, as I said, Ivanhoe Cambridge, architects Wilkinson Eyre from London, England, Adamson Architects. Structural is RJC, electrical model Banani, mechanical TMP, general contractor Ellis Dawn, structural steel Walters, formwork, Structform, rebar Harris. We'll talk about these more, but it was an incredible team. I have to tell you, for many, many, many years, we worked together. There were tough times. Everybody behaved in a civilized manner. We are still happy when we see each other. And I tell you, with the complexity at this level, it's a great result. So let's talk phase one, the tower. The tower is 49 floors, 6 mechanical penthouses, 3 underground parkings, 1.5 million square feet rentable, 54 elevators. Think about it. 8 levels of podium. The podium houses a real bus station, 2-level bus stations, plant rooms, mechanical rooms, food hall, fitness center, conference center. There's a pedestrian bridge on the project, etc. And future connection to the LRT, TTC LRT, I showed it to you. And of course, with bridge to the Scotiabank Arena, former ACC. Some tonnages about, and some data about the project, 130,000 cubic meter excavated. I'm watching my clock as well. 12,000 tons of rebar, 2.2 million square feet of formwork, 86,000 cubic meters of poured concrete, 15,360 tons of structural steel. Think about it. Heaviest truss is 45 meter long, etc. I think that we'll talk. I'll not read everything here, but some canopy is 69 meter long, and Andrew will talk more about the structural steel when he does the overbuild, the podium. So Walters published a little paper about this project in Advantage Steel and talked about and quoted John Frank, the owner's representative. He works for Heinz, and he thinks that this is the most technologically advanced project for Heinz in the last 35 years, and probably this is certainly the most complex in Canada and maybe in North America. And he also commented that a senior VP, John Frank, a very great personality, a great person, by the way, by training an architect. He said that structural steel was the only choice, and it was faster building in structural steel than concrete. We'll talk about that later. And of course, the rail corridor, another great statement by John that it had to be structural steel. And I guess Andrew will talk about it much more. So let's talk about the podium. Now we go, that was the introduction about the project. Let's talk about the podium, how complex the podium is. And you see on the right where my cursor is, that entrance for the bus terminal works now. You can use this. So it's not, it's the podium has Metrolinx's new Union Station bus terminal in there. So Metrolinx did pay part of it for what is there. So yes, it was Heinz, Ivanhoe, Cambridge, but Metrolinx was a partner. So there was a great cooperation with Metrolinx in making this happen. And I maybe missed them, but they were really another great group of engineers there. There is a mechanical plant, food hall, and 3/4 of office building. So look at the complexity. So the tower is on the left side, and to the very bottom left on the screen, you see the overbuild where the trains are. I mean, magnifying this, you see that at the ground floor level, there is a bus. Now, that's the first level of bus terminal. But now the green is a 24-meter span post-tangent slab, flat plate. It couldn't have been thicker because otherwise this elevation would get too high and it couldn't get on the green is matching the overbuild over the rail land. So there were architectural geometrical constraints why we have selected what. It's not just the engineer says, oh, I'll do a PT. Why would you, this is a concrete built below grade, then a PT, then structural steel and everything from here structural steel. So this large span PT for the buses, full story truss for buses, and between the trusses and mechanical systems, and above offices, and very complex, very complex. Yeah. And organizing all this, designing, building on time, super complex. You will see the details now. So this is the podium, Revit. You're building the columns, then you are building the ramps up and down. So here you see it's like a DNA, like a scissors there, by one coming up and going down. And this is the post-tangent slab. Now we are starting with the trusses. But think about it, when you build these trusses and you deck it, when you deck it, you can't put in the big mechanical units. So the big mechanical units were put in before the floor was poured. So the top cords of these trusses were unsupported. Is that right? So you had to temporarily shore them so they don't buckle and you can still install the mechanical units. There's lots of thought going in this in how you design it. And what is interesting is very important for you young engineers that sometimes the support condition during the support conditions of the structural elements during the design is more complex and very different from the final condition. And you have to design for those steps. And that's not as easy because you have to understand what the mechanical engineer is doing and installing the units now and not later, etc. So this is where the teamwork of the consultants are so important. It's not enough to know running ETABS and SAFE. I love those, don't misunderstand. I love 3D final analysis and whatnot, but you must understand why you do what. Anyway, it was a bit long. Here's the mechanical coordination. These are just the ducts. And so then you build up, up, up. This is now our normal, typical structural steel floors. But as you see now, we leave out the columns and there's the big auditorium here in the top and so on and so forth. So that's the podium. And of course, we didn't even talk about the basement. The basement is 3-level underground reinforced concrete, but the loading dock is there. So all these have to straddle the loading dock. But this is the reality here. This is the real picture as you build it. And it's beautiful. And what you see here, this wall with this insane amount of shear elements, I cannot tell you why is it there, but it's a special design consideration for this building. And that's all I can say. I think you might understand, but if not, well, sorry, I can't tell more. Some things are confidential. So this is the PT, level 2 PT. We have 900 PT slab. We have a band of 1100. And this is 90 tons of PT. This is a 7 rounds of shop drawings coordination. It is quite two pours each 18 hours. And look at the PT, the ducts. You see the two directional post-anchoring ducts, and around the steel columns, which were sitting on a concrete below. So it's picked up by a concrete column below. These are the columns above, columns to transfer out on the, and those are the orange ones which go down. And you will see that the steel trusses were located to pick up these columns from above. And this is the 3D trusses you saw. And And this is what you see at the bottom left is the slab in line with the bottom chord, and we had to have continuity. So this is how it looks like. So this is the bottom chord of the truss, but the slab is almost a touch thicker than these bottom chords. And we had to have bar continuity. So these are half length on couplers welded to the nodes, and we had the continuity ensured that way. And this is then a concrete board. And the mechanical units here are not in yet, but so that's the podium. How are we doing? 11 minutes. And I'm at slide 21 to 53. So I'm about 19, 80 more minutes. So let's talk about the tower. The tower is another complex piece of architecture. It's a beautiful architecture. And I will tell you again, and I will tell this because it's true. If it wasn't true, I wouldn't mention. So Wilkinson, Ayer, and Adamson was a charm to work with, and the whole team was great. And the owners were making decisions on time, which is super important. You can have a great crew of architects. If the owner doesn't make the decisions on time, everything is slipping. But there was a great schedule worked out by Alice Dawn and the client and the architects, and we adhered to that schedule. And there were bi-weekly meetings, all-day meetings, and the architects flew in from London, England. It was that serious. Sometimes they called from London, but it's not the same, as you know. So office, 49 stories, 240 meters tall. Again, don't forget, this is exposed to wind because in the rail corridor, the wind is coming from the west. So it's the shielding of the building is not there. Building at King and University, for example, is much more shielded than here. So this is something, of course, it was wind tunnel tested. So this picture on your left on your screen is the original design. Not much different, but look at, this is a real diagram. The columns were diagonal coming down. And this is where the rail goes, and this doesn't go down because this is where the track number 1 is in Toronto. And I think that Union Station has about 50 million people a year coming. You can't stop it. Then there was a shopping mall over the overbuild, which never happened. But this is the overbuild, over the track. And this is phase 1 we have. But what happened is this, and it's very much the same. And so congrats to the architects and the owner that they kept the difference is we don't have a diagram, and that has a very short story. And the short story is very simple. We designed the diagram. It's way too expensive. Toronto market per square feet of office is not New York, and it's not London, England, and it's not Tokyo. So you know, if you only rent for so much per square feet, you can only build for so much per square feet. So that's what is your market. When in Rome, do as the Romans do, and when in Toronto, you can only build what you can sell in Toronto. So it's very important that we understand these parameters. So I will quickly run through some preliminary sketches. Here is this is phase 2, but the bottom knocked out because this is where the train goes. So we had, doesn't want to advance here. Okay, this is another scheme we have done. This is some model, but we have done many ETABS runs on many different schemes with outrigger schemes. Look at the outriggers at the top. Yeah, it's hand sketches, but I want to show you that we start there. We start to imagine these structures in our mind, then we build the ETABS model, then we see if it works, deflection-wise, acceleration-wise, and strength-wise. Always don't miss any of these ever. One doesn't go alone. So this is the outrigger scheme. This is now the current scheme of phase 2, columns coming down, tilting in to avoid getting into the rail corridor. And so various schemes we have done: concrete typical floor, structural steel typical floor, concrete, many beams with concrete. So all kinds of options, and we costed it out and see what's the most efficient and cost efficient. And this is a classic. Day 1, you want to know what's your slab, what your deck on the steel beams, mechanical goes under it. electrical light fixtures are here. What is the sandwich? Can we build this height of tower? And the same with the girders, when the ducts go through the girders, does this work? Day one, you have to, here's a post-tension scheme. Post-tension flat bands, ducts below. And so what is less costly? What is faster to build? Faster to build as well. So now let's look at the tower. We undressed the tower. We took the cladding off. We take the deck off. So we have the beams. Now we took the columns and the beams off. This is the core. This is the lateral load resisting system. The core is in the middle. The core drops off on the right and the south first, then drops off on the left. And as we go up, we have larger floor plate to lease, to rent. Obviously, this is super important. So this is how we built this. And as you see the diamond shape, so this is the core, the elevator cores, and these are the columns, beams, large cantilevers in both directions, moment connections in both directions, not that simple. And you see the edge beam is straight, but you see a diamond shaped building. Every floor looked like this, whether the core dropped off or not. And we decorated the edge every floor differently to give you that diamond or flat pyramid, because this is a very flat pyramid, not with a square base, but with a rhombus. So it's very simple, as you see. And now we add the edge, and these edges are different at every floor to create the module. So, and then this is how typical for build. And so it went this fast. So now this is the real set of documents. This is a real drawing for permit and for construction. And as you see, the straight edge beam and the edge undulates differently, depends where you are, all around. And so you see the core, 12 meters to the perimeter. This is a very classic North American style, Class A office space. 11 to 13 meters from core to the perimeter, no columns, it's Class A. Any columns in between is Class B. And so of course you see the mechanical under the 460 beams, etc. So this is how it looks like in reality. Fantastic location, fantastic site. You see the red props to the core to keep the crane stable. Now I'll flip you some of these beautiful pictures, and some of these, the deck is prepared for concreting, mesh in there. Again, you see the huge props to support a crane. Of course, every construction company wants to save and say, can we just prop this to the beam at the edge and we save all this length? Well, these connection forces are much weaker than the force the crane is impacting. So no, but every job we have to go to this question. And so we are at 27. So this is how it was fire rating. This is the big cantilevers you saw. And these decks from below are not fire rated yet, nor is the structural steel. So the columns. So the columns are, of course, the columns should be small, but look at this. Jumbo sections. Solid 900 by 900 steel columns. We'll show you why. This is about 40,000 kilonewtons supported by this column, if I am right. 24-meter unsupported length in the lobby. Well, yeah, I could have made it bigger, but the architect didn't want this to be bigger. So Euler buckling formula is very simple, is it right? The differential equation is also beautiful. But we couldn't get the EI, the E's inertia is inertia. So we needed the area. And some are composite, some are heavy jumbos in concrete, circular. It really was a complex. Some columns are skewed. So composite columns, as I said, it was 760 solid steel and not 900 by 900. Now, I don't want to spend too much time on this, but this is very important. You see this diagram here on the right, and this shows that the perimeter, the steel columns, elastically shorten a certain way. The right side of this picture, I don't know if this is in your way, I'll move it forward. the right side of this floor is the core, the face of the core. Now, the face of the core shrinks and creeps. Concrete is, let's say, shrinkage and creep occurs in 5 years. Elastic shortening of the steel, well, it's whenever the load is there. Now, the 40th, if the datum of this floor, the datum, look at this where the cursor is horizontal, I have to super elevate, build higher the core so it sinks to the datum elevation in 5 years. I have to over elevate, super elevate the steel columns. So when I build the self weight, we squeeze it back to horizontal. So we tell the client, in 5 years, you will have a horizontal floor. It's like a Swiss watch, but you know that ACI 906 tells you that the shrinkage and creep calculations are plus minus 100% accurate. So don't ever forget to think above 25 floors that there is super elevations going on, because sometimes some people are not doing it to 40 floors, but above 35, 40, you definitely have to think about how much you super elevate to make sure you balance the floor. A very complex topic, but it's enough for you to understand that we deal with lots of complexities on the tall buildings. This is that column that is in the lobby. I guess it's Tom Kasparek, holding onto it. This is the shop from the Cherry Beach. I was shipped to the and so we went to the shop and looked at, this is on the site. But this is the 24-meter column. This is the lobby. And this is tied in at level, I think 5 or something like that. And this is down 20, and this was spliced in the middle. What is the spliced force of this column in the middle, Mr. Engineer or Mrs.? It's not easy because it's not in the code. What is the common practice? What are your loads? Does it want to buckle? What is the buckling load? Etc., etc., etc. And these things are not in the S16 code, and it's not necessarily covered in the curriculum in the university. These are really things that you pick up as you become a senior engineer. This is a few beams. This is some base plates. You can take one home. So we'll show you. So foundation systems, I don't know if you see this. Maybe I should minimize this. All right. So foundation system, we are on WSP was a geotechnical. I have 7 more minutes and I am at slide 30. I should speed up. WSP geotechnical, TerraProbe shoring, and GFL shoring. So we are on a very competitive rock. I think about 8 MPa capacity with a safety factor of about 2.2. So it's a 16 MPa concrete. They're sitting on 16 MPa concrete. We have spread footings and linear footings under the core. We didn't even make a small mat, small raft under the core. There was no reason to. And there's no uplift. So Toronto has a fantastic, in this area, up at Young and Bloor, the rock is 40 meters down. So this is great here. So we go quickly here. Well, spread footings, columns. Of course, now wind tunnel testing. Here's the model, the 10 million measuring points by RWDI, working with them last 2.5 decades. It's an absolute fantastic company. And so are, but they are really the preeminent in the world. We're just showing off some local video about what they were doing here, what the model looks like. That's the other tower, future tower. And all right, so we talked about lateral system, how many elevator banks, how many elevators. Walls are 950 to 500 thickness, 500 at the top, 950 at the bottom, 80 to 50 MPa concrete strength, core setbacks. And what do setbacks do? Look at this. We'll quickly go through it, but I really want you to see this. So if we stop the core here, but we continue, what happens is you're still compressing this, but not compressing that. That creates incredible shear in these coupling beams. These coupling beams, we couldn't make work. We had to make it, these coupling beams, we had to make it from structural steel, because as we were building this, continued building this, this didn't get enough weight. So it's an elastic medium. So basically, we had to go structural steel coupling beams 1, 2, just to make that happen. And embedding these structural steel coupling beams in concrete was not an easy feat. This is how it looks like, looks pretty. And this plate held the concrete in the formwork. Now we had diaphragm actions, of course, because this is the overbuild that has an expansion joint. This is phase 1 with some tilted columns, which we'll get later. And of course, if the core, the yellow, moves east, west, up, down into this 1 meter thick crash wall, and this 1 meter thick crash wall had to be there so the trains moving here don't come into this building. And the crash wall and the proving the crash wall stability and strength with special codes is a whole different topic, and hopefully Andrew will talk about it if I give him time. Yeah, I have 4 more minutes, so I'll run through this. So the diaphragms prop the core, and we have to deal with the diaphragm stresses, and we built the diaphragm trusses, horizontal trusses, to take these loads from the core, pushing into the diaphragm onto the crash wall, which was very rigid. And so other issue is we have columns that are skewed to avoid ramps and loading docks. And so what happens is the insane tension and compression. These tensions that become shear in the core exceed the maximum shear from wind and earthquake. Do not ever forget designing for skewed columns loads, because they are insane. They are large. I mean, okay, take the 30,000 liter and times 0.3, tangent 20 or something, and you will see the load. You have to bring that load into the core here. This is the beam embedded into the core, ties around it, etc. And so we designed a detail, column from above, column below, and a strong plate, but Walters came up with a better detail, have 3 very thick plates and just bolt the flanges to it. So we had our details, we covered the cost, but sometimes, let's face it, Walters is an absolutely world-class company. They would say, hey, I want to do this differently. Sure, no problem, both work. Also connections to the core, when you assume something is pinned. Is this pinned to you? Will not. So you better think about your boundary conditions all the time. You can't just say, oh, it's pinned, but it isn't. It won't behave as a pin. Canopy, we'll run through this because I have to give 4 minutes. The canopy is 69 meter long. These are the special canopy columns, and inside are those very special 750 by 750 structural steel columns. But notice that there is a gray beam here that is a header beam holding these cables. These cables are giving 500 kilonewton per meter tension to this cable wall, so it doesn't flutter in wind pressure. The cable wall is a beautiful architectural animal, beautiful, but it moves the foot back and forth. As it moves the foot, it becomes a cable that is stretched, is moving itself back to the original position. But that is loading this beam and loading this cross beam that loads this beam, this column, which is 24 meter unsupported length, and hence 750 by 750 square. So this is a trellis with glass top. This is the system, and there's this incredible long stair going up to the overbuild across to the north. This is the columns, the beams going back, canopy girders, canopy columns, and then of course this is the cable wall header beam I talked about, and of course you have this that is holding the glass.
Hello, Tibor, we cannot hear you. Tibor, can you hear us?
Seem to have lost him. I'm not sure. Unfortunately, he was controlling the presentation.
Andrew.
Yes, let me see if I can grab him.
Okay.
Or pull up the presentation myself.
Oh, Andrew, can you go continue the presentation?
I unfortunately don't have it up at the moment. I'm just trying to locate it. If you give me 2 seconds, I will present. Sorry, apologies, it's taking a little time to load on my machine. I guess just you have to visualize a little bit, but what Tibor was going on to say about the canopy was there's, because of the deflection of the canopy and wind during service loads, there actually is a fair amount of consideration needed for the deflections in the canopy.
Andrew,
Under a lot of
presentation?
Yeah, I'm sorry, it is loading up. I apologize. I didn't have mine loaded. I'll see if I have a PDF copy because that sometimes works a little bit better.
We have more than 20 minutes. Don't worry.
I have 20 minutes? Okay, I'll rush it. No problem whatsoever. Oh, there's Tibor. He's connecting again.
Here is a man, yeah.
Tibor, are you there?
Tibor, you are muted. You are muted.
So what happened? I am lost. When did I lose you guys?
We lost you.
When?
Just as you were finishing the canopy.
Okay, so fine. Then I would just, shall I share or?
Yes, can you put it back up and I'll,
Yeah.
I think that was the end of your part and I'll take control, I suppose.
No, not that one. Sorry, this share, and I have to run from.
Okay, here we go.
So just to, yeah, so I sort of spoke about the canopy and the deflections. Thanks, Tibor. I'm just going to quickly talk about the items around the main tower project that connect the project to the rest of Toronto. A part of the fact that the GO bus station is within the tower podium and that we are very close to entertainment facilities across Bay Street and close to Union Station really begs for this project to be very well interconnected within the city of Toronto. So one of the ways that was done was connect the podium right across Bay Street with a path bridge that connects into what is now the Air Canada Centre, or sorry, what is now Scotiabank Arena, what was the Air Canada Centre, and you can kind of see it here. This is a very unique bridge. It's probably the most unique bridge I've ever worked on in my career. It's a 40-meter long pedestrian bridge, but it's a open C shape. And for those who are familiar with the consequences of open shapes, they're very susceptible to torsional issues. So we'll just talk about that a bit. There's a lot of steel in this bridge, and really structural steel was the only option here. It's about 172 metric tons of steel within there. Just make sure I can advance here. There we go. So architecturally, the reason why it was an open C shape is because they wanted an unobstructed view down Bay Street, mostly to see their own building, CIBC Square, and the facade, because it runs along this portion. You can see the sort of CIBC Square connection, but also down to the lake and beyond. So that was the goal. there's a few challenges here beyond the open C shape, but we're connecting to an existing structural system at Scotiabank Arena, so that caused some challenges in doing so. So if we break down the structure a bit, you can kind of see what's going on inside. We start with a series of open C moment frames, and the pedestrians walk between those frames down the bridge. This is sort of the system. They are tapered sections. They're in total depth, they're about 1 meter deep at their greatest, and taper down almost to nothing, down to about 200 millimeters at the ends. So you really get this sort of airfoil kind of effect for the structure, and it mirrors the diagonal diamond pattern within the facade of the building. You can kind of see some of the mechanical systems and services in the back there. So you put all those C's together and create a back spine truss, and also a bottom and top truss, and those provide both the lateral resisting system for the truss, but also resist the torsion. So they're doing the work, having this open C shape resisted in all 3 sides, and just from a gravity perspective, and that load gets transferred into the systems at the end. First, at Scotiabank Arena side, we had to do some significant steel work there to reinforce existing columns, which I'll go over in a little bit. And at the CIBC Square side, where we were lucky enough to have a significantly thick concrete element here, that's a 1 meter thick crash wall return. And that's important for the project because of where the forces resolve. This is sort of some of the models we did. Because the bridge wants to sort of rotate downward at its tip because of this open section, we actually did something quite unique here. We, instead of just cambering the bridge as normally we would do to help with the self-weight deflection, we actually cambered it rotationally. So we brought the ends of the bridge high at the tip and sort of had this rotation about the center as we went down the spine. You can see those connection points that I was talking about. The way they erected this bridge was also unique, and I'll show some site photos of that in a moment. It was done in 2 lifts. The first lift was connected to the Scotiabank Arena side, and the second lift was connected to the CIBC Square side, and there was an infill piece done in the middle. So they had to temporarily support the first lift while they put in the second lift. This is some of the photos from the lift. That's the bridge actually traveling backwards along Bay Street, the first piece. So you can see for scale the construction crew here and how large this bridge is. It's about 30 meters long, 35 meters long altogether, and it's significantly wide. It's about 6 meters wide. Some more pictures of lifting the first piece in place, and that's on a tractor trailer that has fully articulating axles. And one of the largest cranes they could get a handle on, actually sitting on the railway corridor that you see above, lifting this into place. There's one more picture of that. That's the second piece. And then you can see the final support condition. So a very detailed structural steel bridge to suit a very high level architectural need to see what's beyond. And there you can sort of see the bridge in its final case. The other aspect that's connecting the project to the city is the overbuild park. So the overbuild park is an elevated park that runs over the Union Station rail corridor. The Union Station rail corridor is Canada's biggest and busiest rail corridor, and with a significant amount of passengers coming in and out every day. This was, of course, pre-COVID, so there's very few right now. It spans over 16 rail tracks, and it is actually second busiest in North America after New York City's Penn Station. The park is beautifully landscaped. There's many elements here for the public to utilize in summer and in winter. It's going to be fully programmable, meaning that there will be events here all year round, and it's connected into both of the phase 1 and phase 2 buildings. If we deconstruct it, this is what's going on underneath. We have the overbuild park. You can see the red line there is an expansion joint. So we're disconnecting the two buildings across the rail corridor and some of the structural elements there. Concrete deck. If we deconstruct it a bit more, you've got our steel truss system below. Interesting, just some notes about the steel truss system, that there's about 100 trusses on the project, and if you stack them end to end, you'd be about 2.5 times the height of the CN Tower, about 1.4, 1.5 kilometers of trusses in total. So a significant amount of steel here used, about 15,000 metric tons. This is some pictures of the overbuild during construction. Large, heavy steel trusses, clear spanning in a lot of cases over the tracks. And some views below. Quickly want to talk about the design of this. The park structure is these large trusses, and they sit on steel columns within the corridor. They are right on top of the platforms that you would use to access the trains. So Metrolinx, who is the rail authority within this corridor, rail corridor, wanted to ensure that they had the ability to offload and load passenger trains at any particular point. But normally they would introduce very heavy elements like crash walls, and we have a crash wall right along the south portion of the rail corridor protecting the actual building. Normally they would introduce these crash walls, but they didn't have the opportunity to do so within the middle of the corridor. So we had to do something a little bit different. The trains primarily coming into this structure are running from the east and going to the west. And so if there ever was a derailment in the corridor, there's the potential that one of these columns, any one of these columns, could be hit by an oncoming train. So we designed the structure to actually have a level of redundancy where this first steel column in the front could actually be removed, similar to what we're going to see in this very short video. And we actually made this video for the client just so the client would understand generally what we're talking about. And it seems quite dramatic, lots of flying debris and what have you. But the structure had to, would deflect under that case. And we had to design the structure to allow for train traffic after a derailment and after a catastrophic event, partly not necessarily for train travel again, but for the ability to have the structure to be repaired and to get the damaged train out of the way. So it's sort of a very unique aspect. And here's some of the engineering we did to look at the column removal and what impact it would have. And we were sort of limited by deflection during that state to ensure that rewriting or emergency work could take place. Another big aspect of this is the pavilion structure. The pavilion structure is supported by this large primary truss. It's a 45-meter long truss. It's about the size of one of those GO train cars that you saw, so about 2 stories tall. And this is the largest truss lift on the project. It connects to the building project over top of the large crash wall there. And the crash wall is also designed for train impact, but of course it can't sustain that. It's meant to design and sustain the impact. It's not meant to be removed or damaged. So there's a lot of work that's gone into the design of that crash wall. But this particular element spans over top of the crash wall and connects into a column that's in the podium and actually causes that column to go into uplift, which was restrained lower down in the foundations. There's that tie down column shown in green. So a very interesting system here. You can see the system on the right-hand side, the big 45-meter long truss, this large beam that spans over top of the crash wall and into that tie down column. That beam is about. There's one of my colleagues. Sorry, mind muting yourself? Thank you. Yeah, so there's one of my colleagues, Benoit, who was also an engineer record on this project, standing next to it. So that's about a 2-meter deep structure. You can see this is it running over the crash wall at night during the lift. This is the crane. It's consequently the same crane that was used to lift the bridge into place. And there's a picture of myself next to the truss, so you can see how tall that is. And all these lifts were done at night by Ellis Dawn in conjunction with the Metrolinx team, because every single track needed to be closed to complete this operation. Quite a feat of engineering, quite a feat of temporary works and logistics. You can see it there being lifted into place. And believe it or not, that big long truss with its connection points, never put into place before at this point, fit almost perfectly. They didn't really even have to adjust the bolts very much. So quite an amazing feat there. There you can see it from above. And this is what it looks like today. It's a little more advanced this is even now, but what's sitting on top of it is a pavilion, and there's supposed to be a sort of high-end restaurant with views of the city from there. So from here, we look, have our gaze from the park into the phase 2 structure, and I'll pass it back over to Tibor to talk about that element of the project.
Thanks, Andrew. Can you hear me?
Yes, we can hear you.
Yes, we can.
Thank
Yeah.
you. Sorry for losing you guys. Not sure what happened. So this is 141 Bay. This is the North Tower. And as you see, this is track 1 where my cursor is. The columns have to come back to the core, and the whole tower wants to tip south. So we took out the left columns as well, and we have this beautiful triangle, as I showed you that picture at the very beginning. This is the trick of this tower. Very, very complicated. And so in reality, this is how it looks like. We have permit drawings, we received the permits. We have special nodes. So for these insane loads sit on concrete, and we don't have bearing problems. And so in 3D, this is how it looks like, because we have the core of 141 Bay. We have the columns coming down vertically, and they all tilt back to the core. And the south face of the core is also an elevator core wall, but a crash wall as well. Like you can imagine. So from the total vertical columns in 141 Bay, only the 2 very west ones and the 2 very east ones go down. Everything else comes back to the core. And so this is how it looks like, with some detailed how design done and how the columns sit and how they are manufactured. Quite a complex process and discussions with the steel supplier. And we don't want to go into these tangent details, but some of these tangents going through the core is in the range of 15, 20,000 kilonewtons. Imagine how much strain, elongation you have in that floor, what happens to the finishes, etc. There's a lot of things to consider here, not just how many bolts do we need, do those bolts fit. So this is the bus terminal, which is demolished by now. This is the south face of one front west building. This is where the new core comes down, and exactly this is what you will see. And this is the core, this is the columns kicking in. And one level higher, the columns are going more to the north and south. And so this is it. It's a picture of Beno and myself. Thank you. And I'm sorry I missed a few minutes there, but not sure what happened. Hope you enjoyed it. Thanks very much.
Okay, thank you very much, Tibor and Andrew, for very, very interesting presentation. Very impressive project. I'm sure everybody enjoyed the presentation. We can open the floor for some questions. If you have questions, put it on the chat. But till we see that, I want to ask you, in general, if you comment on something general. You know, this is a group of graduate students, masters, MEng, MSc, and PhD. So what, Tibor, maybe what advice do you give for the students and they can eventually one day become capable of managing projects of that size and designing projects of that with this complexity?
Thank you. I will try to be short. There's a couple of things that are really crucial. Number one is communication. I really think that you have to know how to talk. It's not about, and I have an accent, I'm an immigrant, but it's not about, of course, correctly, nicely would be best, but you have to know when to speak, what to say, how much to say. If you're not clear in communicating to your colleagues, to the client, to your other peers, you will not go anywhere in life, and you could be a member of a Mensa club, 145 IQ and up. You have, this number one. Number two, you have to think often out of the box. And it's not that difficult to do if you focus on it. Try to understand that problems have different solutions. Yes, there is a typical one, but sometimes you need the non-typical one. Third one, which I find the most important, is never think in elements only. Don't just design a column. Think in systems. Your column is your column.
Please mute
Your
yourself.
column is, so your element is a part of a system. You should always think about a system you design. If you design a beam, talk to the guy who supports your beam. My beam is this. I give you so many moments and shears. Have you considered them? Typical mistakes happen when people don't think in systems, but in elements. So elemental versus system design is one. Second is good communication. And of course, I think the fourth point, and there's many points, but one, again, the most important, very important, you should always be a straightforward, no politicking, honest person. If you don't lie, they will not catch you on anything. Be straightforward, honest, communicate well and clearly. You will go far. Anyway, that's my short answer.
Okay, thank you very much, Tibor. Very valuable. It's very interesting that it's a recipe between being honest in the communication and also knowing when to say and what to say.
And of course, I missed one thing is that, of course, I love complex analyses, vector, final analysis, ETABS, SAP, RAM concept. Yeah, but that's just tools. But how to use the tools, how it fits with the construction techniques, coordination with other consultants. There's a lot to know. This is why it's 10 years to become a senior engineer. And I know young people, oh, but I have done so much. But there's so much to this profession.
Okay, excellent. There is a question which probably I'm gonna expand this question a little bit. The question was about future engineering projects. How will RJC design and build structures in a COVID world in terms of office space?
Andrew?
Yeah, I can feel that. I mean, we have a significant number of clients. I think probably most of our clients are thinking about it now because they need to. And we're seeing a lot of changes in the way programming in buildings is being developed. A lot of emphasis on, especially in our residential markets, emphasis on people having the ability to work from home for some amount of time and having them have that space to do so. So for example, a lot of our, say if you're looking at a 1-bedroom apartment, or they're giving the units a little bit more space than they probably used to. Lobby design is changing. There's a lot of spaces typically built into lobbies and into buildings, both commercial and residential, for co-working, and which is a trend that has people rent out small office spaces, so you can use that. There's some emphasis already on vertical transportation. If we're trying to get people into an office tower in a way that causes them to be separated more, less people using the elevators at once. Well, you maybe need more elevators, or you maybe need a way to manage those elevators in a little bit different manner than you used to. So our clients are definitely looking at these things. Some of these aspects have impacts on the structure, like Tibor mentioned before, maybe larger floor-to-floor plate, or floor-to-floor heights. More elevators obviously increases the area inside the core. Larger lobby spaces increases what we're doing at the ground floor. So it has impact on our structure, but absolutely our clients are definitely thinking about it.
Okay, excellent. So I think we have it to close it now. Thank you very much, Tibor and Andrew, for your valuable time. We know how busy you are and how valuable is your time for everybody. I'm sure you enjoyed the presentation. It's interesting to see both presenters, PhDs, and also a lot of experience. So you can see the value of having a combination of higher education and experience. So at the end, we thank both speakers. Thank you all, and we'll see you next week.
Thank you very much, and be well, keep well.
Yeah, next year we'll have you in person, Tibor and Andrew.
Yes, look forward to it.
Thank you. Bye.
Thank you all.
Bye, everybody. Bye-bye.